Namaskar. Today we will discuss about regional metamorphism of Mafic-Basic rocks. In this we will discuss how a basic composition change during metamorphism right from Zeolite facies up to the Granulite facies. Regional metamorphism of Mafic-Basic rocks. Content, introduction, Barrovian facies, third, type of protoliths, fourth, metamorphism of mafic rocks, and fifth, conclusion. Regional metamorphism is a metamorphism that occurs over a broad area. Most regionally metamorphosed rocks occur in areas that have undergone deformation during an orogenic events resulting in mountain belts that later have been eroded to expose the metamorphic rocks. On the basis of pressure and temperature, we can divide the metamorphic facies into three types, mainly facies of low pressure, second, facies of intermediate pressure, and third, facies of high pressure. Mayasiro originally recognized three different facies series. First, a zeolite, prehnite, pumpelite, blueschist, eclogite type. Second, a typical Barrovian type characterized by Greenschist, epidote amphibolite, Granulite type characterized by paragenesis of kyanite, sillimanite type, and third, an Abukama type of Greenschist, Amphibolite, Granulite characterized by the paragenesis of Andalusite, sillimanite type. Regional or Barrovian metamorphism cover a large area of continental crust, typically associated with mountain range, particularly subduction zone or the roots of previous eroded mountains. The regionally metamorphosed rocks cover during an orogenic events the collision of two continental plates or iceland arcs, with continental plate produce the extreme compressional forces required for the metamorphic changes typical of regional metamorphism. The facies of intermediate pressure or Barrovian type are listed below in order of increasing temperature and pressure of metamorphism. That is, first zeolite facies, second is your Greenschist facies, third is your Amphibolite facies, and fourth is your Granulite facies. The Barrovian facies series occur in a number of Paleozoic mountain belts as well as in some of the Precambrian age. The classic region in the Scottish Highland. Other belts with a Barrovian rocks occur in Colorado, British Columbia, Alaska, Venezuela, Spain, Southern Europe, Asia, Japan, etc. Precambrian belts of Barrovian rocks occur in the Black Hills of South Dakota, the Rocky Mountains, Labrador, Ontario, Canada, and the Singhbhum in India. The Paleozoic orogenic belts are clearly associated with convergent plate margins. Both Barrovian and the Bookend facies series developed as such margins. In convergent zones, regional heating due to rise of plutons into the overlying plates, the plate above the subduction zone, is the general cause of metamorphism, but migrating fluids may also be transport heat. The zone of metamorphism in the Scottish Highland, originally described by Barrow in 1893, includes 6 index minerals, that is chloride, biotite, almandine, garnet, stellite, kyanite, sillimanite, etc. The lowest grade in the geolite facies, which form under condition just above those of the diagenesis assemblages, is characterized by the clay minerals assemblage, may include kaolinite, illite, chlorite, quartz, analcite. At slightly higher grade condition, assemblages of the geolite facies are replaced by those of the prehnite, pumpelite facies. As the same PT condition increase, the Greenschist facies assemblages with new minerals form. Typical assemblages in peltic include white, mica, chlorite, chloritite, quartz, albite, magnetite, biotite, epidote, garnet, pyrophyllite, kyanite in an almandine zone of Greenschist facies. The Greenschist Amphibolite facies boundaries is a broad zone. The disappearance of albite marks the maximum upper limit of the Greenschist facies. Thus, albite, like pyrophyllite, is absent from Amphibolite facies rock. Stolite rather than chloritite occur in the lower part of the Amphibolite facies, and aluminum silicate, kyanite at lower grade and sillimanite at higher grade characterize aluminous bulk composition. The Granulite facies is distinguished by the general absence of white mica and presence of orthopyroxene and plus minus cordite. The pre-existing chemical composition of the rock is responsible for the mineralogy of its metamorphic offspring. When we normally study the metamorphic rocks, it is essential to keep in mind about the parental composition of the rock. In fact, the chemical composition of the rock protolith can only provide the important clue towards deducing the parents. We can keep certain sedimentary and igneous rocks into 6 important compositionally based groups. First, ultramafic rocks, mantle rocks, cometite and cumulates, very high Mg, Fe, nickel and chromium. Second, mafic rocks, basalt, gabbro and some gravax, high Fe, Mg and calcium. Third, salts or peltic rocks, the most common sediments, fine grained clastic clays and silt deposited in a stable platform of or offshore ways, high Al, K and Si. Fourth, carbonates or calcareous rocks, mostly sedimentary limestone and dolostone, high calcium, magnesium and CO2. Fifth, quartz rock, cherts are oceanic and sands are moderately high energy continental clastic, nearly pure SiO2. Sixth, quartzo-feldspathic rocks, arkose or granitoids and rhyolite rocks, high Si, Na, K and Al. Although these 6 categories are to a degree gradational and they cannot include the full range of possible parental rocks, but they do cover most types which are responsible for metamorphic perspectives. Amphibolite, a metamorphic rocks dominated by hornblende plus plagioclase. Amphibolites may be foliated or non-foliated. The protolith is either a mafic igneous rocks or gravax. Ascola define metamorphic facies on the basis of metamorphosed mafic rocks, also called metabasites. Characteristics of minerals. The principal minerals changes in metabasalts are due to the breakdown of two most common basalt minerals, that is plagioclase and clinopyroxene. As temperature is lowered, the more calcic rich plagioclase, the high temperature igneous plagioclase in the albite anorthite system becomes progressively unstable. The low metamorphic grade, only albite anorthite 0 to 7 is stable. In the upper Greenschist facies, oligoclase anorthite 7 to 17 becomes stable. The anorthite content of plagioclase thus change from 0 to 7 to 7 to 17 as the grade of metamorphism increase. Andesine and more calcic plagioclase become stable in the upper Amphibolite and Granulite facies. Clinopyroxenes break down to number of mafic minerals. These includes chlorite, actinolite, hornblende, epidote and a metamorphic pyroxene, etc., and are commonly diagnostic of the grade and facies. For the regional metamorphism of Mafic-Basic rocks, we have to compare all the facies of intermediate pressure, that is Zeolite, to granulites in view of major change in mafic rocks only during metamorphism. Regional metamorphism of Mafic-Basic rocks during Zeolite phases. Very low grade metabasites are usually partially altered to a very fine grained rocks. Prior to the work of D.S. Clumes and co-worker in New Zealand, such rocks were written off as altered and did not receive much importance from petrologists. In New Zealand, during Zeolite phases of metamorphism, volcanic glass is altered to the zeolite hollandite along with clay minerals like kaolinite, montmorillonite plus secondary quartz and carbonates. We can find out the important mafic assemblages during zeolite phases metamorphism with the help of ACF diagram. The first assemblage is your chlorite plus hollandite or lomentite plus calcite plus quartz plus albite. Further increase of pressure and temperature, the zeolite phases move towards prehnite, pumpelite phases and actinolite. During this change, we can observe the following assemblages: assemblage 2, chlorite, prehnite, calcite, and assemblage 3, pumpelite plus actinolite plus chlorite in upper part high grade. Further increase of pressure and temperature, the pumpelite disappear as rock enter the Greenschist phases, where it is replaced by actinolite plus epidote. Important reaction: first, analcine plus quartz give rise to albite plus water. Second reaction, hollandite give rise to lomentite plus quartz plus water. Third reaction, lomentite plus calcite give rise to prehnite plus quartz plus 3 water plus CO2. Reaction number 4th, lomentite plus prehnite plus chlorite give rise to pumpelite plus quartz plus water. Reaction 5th, pumpelite plus calcite plus quartz give rise to epidote plus actinolite plus water. The Greenschist phases include the common products of low-grade regional and dislocation metamorphism. The metamorphism of mafic rocks is first evident in the Greenschist phases, which correlate with chlorite, biotite and almandine zones of the associated peltic rocks, although relate igneous textures may be preserved. The mineralogy reflect re-equilibration to metamorphic condition. Greenschist facies are characterized by the abundance of green color minerals, for example, chlorite, epidote, actinolite and quartz. The association of albite and orthite nearly 7 and epidote is a characteristic of this facies. Furthermore, chlorite in the presence of quartz and muscovite. Other diagnostic minerals are mica, muscovite and biotite, microcline, pyrophyllite, kyanite, garnet and hornblende, etc. Mafic-Basic assemblages in chlorite zone. We can observe the following basic assemblages with the help of ACF diagram. Assemblage 1, albite plus epidote plus chlorite plus actinolite / tremolite plus minus quartz. Second, basic assemblages in biotite zone. There is no major change in basic assemblage or mafic assemblage during biotite zone of Greenschist facies. The basic assemblage is same as in chlorite zone, that is albite plus epidote plus chlorite plus actinolite plus minus quartz. Mafic and basic assemblage in almandine zone. During almandine zone of Greenschist facies, almandine rich garnet and hornblende appear for the first time by the following reaction. FeMg chlorite plus quartz give rise to almandine plus Mg chlorite plus water, chlorite plus actinolite plus epidote give rise to hornblende plus water. We can observe the following mafic/basic assemblies with the help of ACF diagram. First assemblage, hornblende plus epidote plus albite plus minus quartz. Second assemblage, hornblende plus epidote plus almandine garnet plus albite and plus minus quartz. In the higher pressure of Barrovian zone, hornblende appears before oligoclase and a transitional albite epidote hornfels facies proposed by different workers including Ascola may be useful in higher PT terrains, in low pressure temperature terrain and in contact areoles. The plagioclase transition occur first. Metabasites in the Amphibolite facies are characterized by the assemblage hornblende, plagioclase and orthite more than 17% with less amount of quartz, epidote, garnet, clinopyroxene and biotite. Epidote usually disappear in upper Amphibolite facies, that is stolite, kyanite, sillimanite orthoclase zone in associated peltic rocks. In an ACF diagrams, we can observe different mafic/basic assemblages during this phases of metamorphism, right from stolite zone, kyanite almandine zone, sillimanite muscovite zone and sillimanite orthoclase zone. Mafic/basic assemblages during stolite zone. Assemblage 1, hornblende plus plagioclase plus almandine plus minus epidote plus minus quartz and plus minus biotite. Assemblage 2, hornblende plus plagioclase plus minus epidote plus minus quartz and plus minus biotite. Assemblage 3, hornblende plus diopside plus plagioclase plus minus epidote plus minus quartz and plus minus biotite. The derivative of mafic/basic rocks in Amphibolite facies, many of them are garnetiferous, coexistence of plagioclase, anorthite 25 to anorthite 45 with epidote is a common in these rocks. Important reaction. Reaction first, tremolite plus 3 calcite plus 2 quartz give rise to 5 diopside plus 3 CO2 plus water. Reaction 2, tremolite plus chlorite plus quartz give rise to hornblende plus anthophyllite plus water. There is no major change in assemblies of mafic/basic rocks. Changes during metamorphism of other zone of amphibolite facies, that is kyanite almandine zone, sillimanite muscovite zone and sillimanite orthoclase zone. The Granulite facies is characterized by the presence of large anhydrous mineral assemblages in metabasites. The important mineral assemblages is orthopyroxene plus clinopyroxene plus plagioclase plus quartz. Garnet is also common and minor hornblende and or biotite may be present. Hornblende may remain stable in metabasites in the lower Granulite facies, but dehydrates in the upper Granulite facies. The texture is generally gneissic and grain shapes are granular, thus bearing no resemblance to the original basalt. The origin of Granulite facies rock is complex. Granulites represent unusually hot condition. They present temperature excess of 700 degrees centigrade. Important reaction: a number of metamorphic reactions have been suggested to count for the diagnostic appearance of orthopyroxene. Reaction first: anthophyllite break down and give rise to orthopyroxene plus quartz plus vapor. Second reaction: hornblende plus quartz give rise to orthopyroxene plus clinopyroxene plus plagioclase plus vapor. Third reaction: hornblende plus almandine garnet plus quartz give rise to orthopyroxene plus plagioclase plus vapor. Disappearance of hornblende and anthophyllite marks the beginning of the Granulite facies. Basic and mafic assemblies during Granulite facies. The important assemblages we can observe with the help of ACF diagram is as follows. Assemblage 1: hyperthin plus plagioclase plus minus quartz, that is also known as anderbite, that is basic charnocite. Second assemblage: hyperthin plus plagioclase plus garnet plus minus quartz plus minus orthoclase, that is also anderbite, basic charnocite, garnet bearing. Third assemblage: hyperthin plus clinopyroxene plus plagioclase plus minus quartz, 2 pyroxene granulites, because in this case both pyroxene are present. Fourth assemblage: clinopyroxene plus plagioclase plus minus quartz. The course content on a regional metamorphism of mafic/basic rocks begin with the introduction, followed by the description of introduction, characteristic of mafic rocks, metamorphism of mafic rocks with a detailed comparison from geolite to Granulite facies with the help of ACF diagrams, important reaction and changes during prograde metamorphism of mafic rocks. Thus, on the basis of the detailed study of different subfacies and also with the support of experimental data, we can conclude that during prograde metamorphism of mafic rocks, metabasite, amphibolite and 2 pyroxene basic granulites are formed. Thank you very much.